Hello everyone, I'm Kashif Rabbani. I'm going to present our paper Extraction of Validating Shapes from Very Large Knowledge Graphs. Co-authors are Matteo Alessandrini and Katya Hos. Knowledge graphs depict knowledge in terms of entities and their relationships in a dynamic and data-driven way. They represent information in the form of triples, such as subject, predicate, and object. For example, in this example knowledge graph, Da Vinci is an artist and he painted the famous painting of Mona Lisa, which is located in Louvre Museum. Knowledge graphs are adopted in the industry at a very large scale, and they can easily reach billions of facts, as shown in this example table. Usually, knowledge graphs are created by curating data from various heterogeneous data sources, and then various kinds of analytics are performed over them by executing Sparkle queries. The question is, how can we ensure the quality of the data in the knowledge graph? Specifically, we can ask how to validate the data in the knowledge graph and how to avoid insertion of erroneous data during the data ingestion phase. And the answer is by using validating shapes such as Shekel and Shex. Shekel became a W3C standard in 2017, and it is a constraint language which helps defining constraints of data for the validation purpose during the data ingestion phase. Now the main question is, how can we define validating shapes? The most reliable way is to define them manually. However, knowledge graphs are very large in size, up to hundreds and millions of entities and hundreds of thousands of classes, for instance in Wikidata. Thus, they require too much manual effort to define shapes manually. Let's define shapes constraint for an example knowledge graph. This knowledge graph represents information about a university student, Bob, who is taking a database course advised by a full professor, Alice. Let's define validating shapes for this graph. At first, we identify classes. This graph contains 6 classes. Then we identify properties with their cardinalities. But here, we differentiate properties having literal object value and non-literal object value. For example, this node, database, it has a property name with value of type literal string. So we will identify all such cases and associate such properties to their respective node shapes with the cardinality. For non-literal object type properties, such as Alice, who is a full professor, having a property teacher of with object value as of type node, which is non-literal, it is an IRI, we will connect node shapes with their respective association and cardinalities, such as shown in this figure. Altogether, this network of constraints represents validating shapes. And this is the Shekel syntax for full professor node shape, having 3 property shapes of type literal, IRI, and another IRI. Now that we have seen it is cumbersome to manually define shapes for graphs having thousands of classes and properties, we explore the existing automatic approaches to derive shapes from the data, but the existing approaches derive shapes by trusting the data, which results in compromising the quality of the output shapes. Because knowledge graphs are usually created by crowdsourcing and using ETL pipelines, thus they are prone to contain errors. Let's see an example of spuriousness. We will use the subgraph of student from an example knowledge graph. In this subgraph, as an example, if a spurious property street is associated with Bob in the knowledge graph, this will result in extraction of spurious property shape in the extracted set of validating shapes. So, if the shapes are extracted from the data and the data contains errors, such errors will result in spurious properties. Quality concerns are one of the challenges in existing shapes extraction approaches. Such approaches are also not able to handle shapes extraction from very large knowledge graphs and have limitations on the commodity machines due to large memory footprint. To solve the challenges of huge size and limitation of a commodity machine, we propose scalable and efficient algorithm for shapes extraction. To deal with the quality issues, we introduced the concept of support and confidence in shapes extraction, inspired by the frequent pattern mining. Altogether, we propose a quality shapes extraction approach called QSE. Let's see how we define support and confidence. Support refers to the relative frequency of an item set in a data set. Here, the support of a node shape is defined as the number of entities of a specific type of class. For instance, if this example graph has 10 students, the support for the node shape would be 10, and 5 out of them are taking course, the support for the takes course property would be 5. Similarly, the confidence is the ratio between how many entities conform to a specific constraint over the total number of entities. So in this case, the confidence for the takes course property would be 5 by 10. This slide shows the overview of QSE approach. Given a knowledge graph, it can automatically extract shapes with support and confidence, and then user can provide various pruning thresholds to get reliable set of shackled shapes to be used by a validator and get the validation report. Specifically, QSE has two variants, QSE exact and QSE approximate. Let's see the working of QSE exact approach. Exact approach consists of 4 phases. In the first phase, entity data is extracted by parsing the type tuples with their types and frequency. For example, here in a small example of a knowledge graph, Bob is a student and a person. So in the first phase, it will extract that there exists entity of type student and a person, which is Bob, and the total number of students and the persons in the graph. Moving further, in the second phase, it will extract the property-related data for all the extracted entities. For example, now for Bob, it will extract its properties with their object types, such as name, having object type string as literal, email, having object type string as literal, and text course, having value databases, which is a non-literal object type of type course. This way, QSE can handle combinations of multiple properties having various literal or non-literal object types during the shapes extraction phase. Once we have extracted entities and the property-related data information, in the third phase, we compute support and confidence. For example, the occurrence of entities of type student having property name with object type string, which accounts for support, and their relative value with respect to the total number of students, which counts for confidence. And finally, the shapes are constructed in the fourth phase with the user provided pruning thresholds for support and confidence. Although exact approach is able to extract shapes, it has some limitations because when using very large knowledge graphs, space grows linearly to the number of entities, which results in a memory limitation, and thus unable to support extraction of shapes from very large knowledge graphs. Therefore, we have proposed an approximate version of QSE. In approximate variant, the main difference is in the first phase, where we use dynamic reservoir sampling to extract entities. Reservoir sampling is a method for selecting k random samples from a stream of data in a single pass, ensuring each item is equally likely to be chosen. When sampling entities using dynamic reservoir sampling, the algorithm creates one reservoir per type. For instance, Bob is a student, so the algorithm creates a reservoir for student and inserts Bob into it. Similarly, Alice is a professor and a chair, so the algorithm creates two reservoirs and inserts Alice into both of them. Precisely, in our approach, we have one reservoir per type. The size of the reservoir is not fixed. This is not the standard reservoir sampling, because classes can have skewed number of instances. Therefore, we use dynamic reservoir sampling, which starts with the lowest possible size and increases dynamically. After sampling entities, entity property related data is extracted from the sampled graph in the second phase, and support and confidence values are estimated with respect to the sampled graph, and so on and so forth. We have evaluated our approach on various large-size datasets. We will present the result on both of its variants. such as runtime and memory consumption, and the quality of the output. We also have two variants in QSE. One is file-based, which expects RDF graph files as input, and the other is query-based, which uses SPARQL endpoint and queries to extract shapes. We used DBpedia, LuBM, Yago 4, and two versions of Wikidata for experiments. Wikidata from 2021 is the largest dataset we have, having 1.9 billion triples, 91 million entities, and 82,000 classes. We used a machine with 32 cores and 256 GB RAM to run the experiments. Timeout was set to 24 hours. Results were compared with the existing shapes extraction approach called Shexer. QSE exec took only 3 minutes to extract shapes from DBpedia, which contains 52 million triples and 5 million instances, while the approximate variant only took 1 minute. Shexer took 26 minutes. The memory consumption for QSE was less than 16 GB for both variants, while Shexer required 18 gigs of memory. On Wikidata, Shexer went timeout. QSE exec took 2.5 hours with 235 gigs of memory consumption, while approximate took only 1.3 hours with 32 gigs of memory. These results show the efficiency of our approach. This table shows the statistics of shapes extracted from each of the dataset. For Wikidata, it extracted 82,000 node shapes and more than 2 million property shapes. To prove the effectiveness of using support and confidence to prune spurious shapes constraints, we set support greater than 100 and confidence greater than 25% and extract shapes from DBpedia datasets. Using these thresholds, QSE was able to prune out 15% of spurious node shapes and 83% of spurious property shapes. Thus, pruning helps identify spurious constraints, especially for property shapes. We measured the quality of the shapes extracted using approximate approach by computing precision and recall. This table shows the results on Wikidata, which contains 1.9 billion triples and 91 million instances with 82,000 classes. So this table shows sampling percentages ranging from 10 to 100 with various limits of reservoir size having minimum support 1 and confidence 25%. So it shows that QSE approximate is able to sample and extract shapes with 92 to 100% precision with respect to the real graph. Specifically, for 100% sampling percentage, it was able to extract shapes from Wikidata in 98 minutes using 32 gigs of RAM with 100% precision and 92% recall. This shows that approximate approach can extract quality shapes constraints. To sum it up, we have proposed an approach to extract shapes from very large knowledge graphs, which is scalable. It uses dynamic reservoir sampling, and it is able to provide measure for the quality using the notion of support and confidence. All the resources and details are available on our website. Thanks for listening.